So thus far, we've focused on isometries, which are rigid motions that preserve all side measures and angle measures. We did congruence transformations by using reflections, transformations, and rotations. Those preserve the same shape. Today we're going to change the size of the shape through what's called a dilation. So a dilation with center of dilation C and a scale factor n is greater than 0 can be written as Bn comma C. It is an enlargement or reduction of a figure that preserves angles and creates similar shapes. So the shapes aren't going to be the same size. Right? They're going to be either larger or smaller. So if I have a scale factor n that is between greater than 0 but less than 1, this is a reduction. It's going to make our shape smaller. It's going to reduce it. But think about it like this. If you multiply a number by a number between 0 and 1, it's going to make a smaller number. For example, if I take 4 and multiply it by 1/2, what's my answer? What's 1/2 of 4? 2. So a reduction is going to make our number small. You can think of it in that idea of a fraction. If n is greater than 1, we have an enlargement. So we're going to have our figure get larger. Right, so think of multiplying a number by, say, 3. So what's 4 times 3? Is it going to get smaller or bigger? Bigger. It gets to 12. Right? Well, that's an enlargement. So, reduction. Scale factor. N is between 0 and 1. And enlargement. The scale factor. N is greater. So going down to this one, we have a dilation of n comma 0. That 0 is at the origin. And just like when we were rotating about the origin, dilating about the origin makes it real easy to go ahead and find our figures. So we have the black is the pre-image, and the blue figure, J prime, K prime, L prime, N prime, is the image we ended up. So are we getting smaller or bigger? Smaller. So this is a reduction. Right? This is a reduction. So I want to figure out the scale factor of the reduction. So I want to figure out what n is. So a nice, easy way to do this, right, is let's figure out scale factor. That scale factor n. We're going to do our side length of the image over the side length of the pre-image. So in this case, I'm going to look for any sort of horizontal or vertical lines. Why? Because it makes it really easy to figure out the distance in our coordinate plane. If I were to do these diagonal ones, I'd have to either use Pythagorean theorem or the distance point. Do I have any vertical lines? Sure. K prime, L prime, and KL. So n, the side of the image right here, see? And then the side length of our pre-image where we started, 1, 2, 3, 4. go ahead and simplify that. So my scale factor is 1/2. So this is a dilation, and the scale factor always comes first. 1/2 about the origin. So now I want to figure out the coordinates as I go ahead and blow this thing up, right? So I have a dilation of 2, and whenever we don't see a point for the center of our dilation, we can assume that the dilation center is the origin. So this is real easy to do. First thing I'm going to do is, just like I did with rotations, is write down all of the coordinates of the points. So I want to figure out what P, Z, and G are. P at 2, -1. G, 0 to -2. And Z, -2. Find all the coordinates of our vertices. And to find P prime, Z prime, G prime, I'm going to take the scale factor and just multiply it by everything. So 2 times 2, 4. 2 times -1, -2. 2 times 0, 0. 2 times -2, -4. -2 times 2, -4. And 2 times 1. So now I'm going to graph each of these. P prime. We have 1, 2, 3, 4, -2. That P prime moves all the way out. Z prime. And I mix these two up. So there we go. G and Z here should be G prime and Z prime. There we go, that's fixed. So G prime is 0, -4, so there's -3. -4 is going to be there. There's G prime. And then Z prime, -4, +2. There's my Z. And I can go ahead and connect these dots. And notice all the angles are going to be the same on there, right? Because they are similar. Remember our definition of similarity. We had all the angles are congruent, and the sides have a common ratio, right? That scale factor, right? In this case, 2 to 1. So if I did, let's see if I can go ahead and line this up. Line up these angles. Notice all the angles are congruent. They fit perfectly. However, our dilation is an enlargement, so it's much bigger than the previous. All right, continuing on. 9.7 is on similarity transformations. So we looked at congruence transformations in 9.5, where we did a composition of rigid motions. So when we combine translations with reflections or rotations, or any combination of those three, we found that we could prove two figures are congruent to each other. Just as we learned in chapter 7, we can prove figures are similar too. Remember, if we can show that two angles of one triangle are congruent to two angles of another, we can show those triangles are similar at least, right? And then that common scale factor, right? We use side angle side or side side side, show that they have a common scale factor of the sides, and we can prove triangles are similar in that regard. So a similarity transformation is just a composition of a rigid motion with a dilation. So if I have a dilation with a translation, or a dilation with a rotation, or a dilation with a reflection, these are similarity transformations. And I can prove figures are similar through a series of transformations, as long as one of them is a dilation. All right, let's just move on over. I'm going to graph this triangle L, M, and N. So I have L, -4, 2. M, -3, -3. And N, -1, -. And I'll connect these vertices. Here's my triangle. So let's see what the question is asking us. Suppose the triangle is translated 4 units right and 2 units up, and then dilated by a scale factor of 0.5. All right, so remember, we go right to left whenever I'm doing compositions. So we're going to start with our big T. I'm going to write it just like this. And it's translated 4 units to the right, so that's a +4. And then 2 units up, +2. And then our composition, and dilated by a scale factor of 0.5 centered at the origin. All right. Sketch the resulting image of the composition of transformations. Is this a congruence or similarity? Well, if it's the same side that's congruent, ends up being a different side that's going to be similar. They don't have an anticipation whether it's going to be similarity or a congruence transformation. It's going to be similarity because the dilation's involved. So let's go ahead and do this. So I need to first figure out where each of my points go based on this translation. I'm going to move L over 4 and up 2. 1, 2, 3, 4, up. There's where my L ends up. I'm not going to put an L prime there yet, because I need to go ahead and do an intermediate step. Over 1, 2, 3, 4, up 2. There's an N. And then over 1, 2, 3, 4. All right, so there's the result of the translation. So remember, we always do our translation first, and then our dilate, going right to left. Do the translation first. So what I'm going to do to make this easy on me is to go ahead and let's go ahead and graph those intermediate, or find the coordinates of those intermediate points. 0, 4. M is 1, -1. And N is 3, 1. Now I'm going to take this scale factor of 0.5 and multiply everything down both of these, all of those coordinates by 0.5. So L prime, 0 times 0.5 is 0. 4 times 0.5 is 2. M prime, 1 times 0.5 is 0.5. Negative 1 times 0.5 is negative 0.5. And then n prime, 3 times 0.5 is 1.5. And then 1 times 0.5 is 1.5. Now once I graph those points, I'm going to shade in my final resting spot of the dilation from 0 to, there's my L time, and 0.5, negative 0.5. Right in there, there's my M prime. And then 1.5, 0.5. There's my N prime. There's a little baby triangle in there, since it is a reduction, right? Because that is less than 1, is the image of that composition of transformations. So this guy right here is where we ended up. We translated and then shrunk. So we can perform a composition of transformations, but one of the main things we want to do is be able to show that two figures are in fact similar by stating a composition of transformations. All right, let's see if we can do this similarity one. All right. So typically, what I'm going to look for first is, let me first see if I can get the shapes the same size. So let's perform our dilation first to see if I can get those shapes the same size. All right. So what I'm going to do is see if I have a horizontal or vertical line, and then see if I can find that scale factor. Remember the scale factor? N is length of image over length of pre-image. So I just need to find one of the sides to find that scale factor. The scale factor is just the ratio of corresponding sides to similar figures. So I'm going to first look right here. I have AB and M. So which direction am I going? Is this going to be a reduction or an enlargement? Well, it turns out we need to figure out which one we're starting at. So what is the composition of rigid motions and in a dilation that maps ABCD onto trapezoid MNHP? So we want to go from the big one to the small one. So this is going to be a reduction. It's going to be a reduction. So our scale factor is going to be the image and M over the length of the pre-image AB. So I have 2 over 1, 2, 3, 4. My scale factor is 0.5. So let's go ahead and perform that and go ahead and shrink ABCD. So remember what I'm going to do. I'm going to find each of those points. -6, -2, 2, C, -1, -2, and D, -8, -2. Once I have each of those, I can multiply them all by the scale factor. This will give me ABCD reduced. So I have negative 3, 1, negative 1, 1, negative 0.5, negative 1, negative 4, negative 4. Give me a second to jot those down. We'll go ahead and graph those and see if I need to either translate it over to map ABCD on top of MNHP, or if I need to do a reflection or possibly a rotation. I'm going to graph these. There's B. There's C. And then D. All right. Then it's fairly clear now that these guys aren't oriented the same, so I can't just translate one on top of the other, right? So I'm going to look to see if I can do a reflection. My line of reflection is going to be right there, that y-axis. So let's see if it will map on top of the other one. Use this color. So one in this direction. There we go. Half one in that direction, and then 1, 2, 3. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4. So we have a composition of a dilation and a reflection. We're going to write that as follows. So we first dilated, right? And we said the scale factor was 0.5. And we dilated that about the origin with a composition of a reflection across the y-axis, which is the equation of line x equals 0. So we can say that ABCD is similar to MNHP. By the composition of a dilation and then reflection. Thank you. Please tell your friends.